pero las respuestas van a ser en inglés. Okay, so this is the second class on differential analysis of flow. We already covered fluid kinematics, although I think we could go a bit into more detail into potential flow that we just discussed it very briefly. So a bit of housekeeping. We're probably going to have a quiz, a reading quiz next Monday. I will let you know through Canvas. Evaluating these two units, the unit 3 and 4 on fluid kinematics and differential analysis. Those of you that didn't turn in the English writing skill, I still don't know what's going to happen with that. The university has to tell me yet. And those of you that did turn it in, I'm still waiting for the feedback from the university, telling who's got it right and who's got an acceptable level of writing and who needs to improve. So I'll keep you posted on those news. And I don't know, I expect to have something during this week. And lastly, if you want to review your first midterm, you have time until, let's say, tomorrow. This is not very fixed, but I think we've had already enough time. So if you want your test to be reviewed, just let me know in an email without much detail of what you did. I mean, just let me know, this was wrongly assessed, and I want you to count the points again, and we'll do just that. But no further explanation is needed. Okay, so today we're going to finish up the differential analysis method. Just as a brief summary, we've been talking about the Euler equations. Do you recall? The Euler equations, and later on we saw the Navier-Stokes equations, right? Euler is for inviscid flow or ideal flow. This is flow that doesn't have viscosity. Navier-Stokes equations include the viscosity terms due to some higher order derivatives, right, that involve viscosity. Now, when do we use one set of equations or the other depends mostly on the importance that viscosity has. So if it's normally water and and you have very large velocities, then viscosity is not very important. So you can describe the flow with the Euler equations. On the other hand, if you're talking about, let's say, honey or a syrup or something like that, or paint paint, and you have very small velocities, then, well, viscosity is pretty important. So then you need to describe the flow using the Navier-Stokes equations. Okay, but now that's pretty, that's qualitative. So we can do this more quantitative. So let me show you now. Wait, let me show you now this. Can you see my screen or not yet? Can you see it? Yes. Excellent. Okay, so this is I already uploaded the slides for today, I think, or I didn't. I think I didn't, right? But yeah, I'm sorry. I will post them later. But today we're gonna have a pretty whiteboard class. So what I wanted to show you is you're going to be able to see the slides later on and to read the rest of the chapter on the book. So I'm just going to discuss with you briefly about this difference between when you use one set of equations and the other, and then we're gonna do an exercise. Okay, so that's going to be for today. Also, in line with what we talked last week, I'm going to try to keep the class short, around 2 hours, not too much more than that, because I realize it's late in the day and it can get very repetitive and quite long to suffer. So I'm going to try to keep it on point. Okay, so What I'm going to show you now is a replication of a very old experiment carried out by uh, an English scientist called uh, Osborne Reynolds. So what you have here, don't mind much about the details, but what you have here is a tank in the upper part, and then you have a pipe, a transparent pipe coming down the tank, and you can control. You have this valve on the bottom, and you can control how much water is going down. So this tank, what you aim is to have a constant head. Remember when we talk about business, you have the velocity head, you have the position and the pressure head. So the total energy is expressed as a head because it can be expressed as a unit of length, right? Of a height. So you can, when we talk about energy in fluids, we normally talk about meters. So that's why we use the term head. So in this tank, you can keep the head um, constant. And and what the experiment does is that they are injecting a bit of ink, or is a dye, is another fluid that's more sticky than water, typically ink, uh, in order to visualize the flow. So you're injecting the ink into the flow, and then you're opening the valve at the bottom in order to make the the fluid flow. Okay, so now you can see how the ink is going down because it has this initial mixing, and what we want is to have all the ink going right down in order to be able to see this ink. Okay, if you recall, at the beginning of chapter 3 we talk about uh, smoke lines, uh, streamlines, and path lines. Do you recall? What kind of line would this blue line would be?
A streamline.
Well, we technically it's a okay. We have streamline, we have path line because experimental. Well, technically it's a smoke line, right? Because we are painting all the particles that are passing through one point. So that's a smoke line, all right? And do you recall when streamlines, path lines, and smoke lines were equivalent? Do you recall what had to happen? Steady flow. Yeah, steady flow means no change over time. So yeah, we need steady flow. We also need irrotational flow, right? Because as you're gonna see, you can have steady flow and still this thing don't be the same. Okay, so this is, have a look at this. This is a very uniform line. Basically, let's say this is at the center line of this pipe. Down the line is more or less still around the center. It doesn't change much along the pipe, right? So basically, if you take a cut in one section and compare it to another section, they look pretty much the same. So here clearly we have steady flow, right? And what you cannot see here is that in this case, the valve at the lower end, at the bottom, is open just a little. So you have a very small flow flowing. Okay, it's very small flow. Um, so it's just a slight flow, very small, and that keeps the ink more or less at the same position. You can see it's just a tiny bit of water. Well, here they are just measuring how much water is going out. It doesn't really matter. Now the guy or girl, I don't know, is just increasing the flow. So he's opening the valve a bit. And what's going to happen is that you're going to have more water flowing. And look at the line near the exit of the ink. it stops being so uniform and it starts moving a bit. Can you see it? Here, do realize that we still have steady flow because the flow is not changing over time, but we have these random fluctuations inside the pipe. Okay. Uh, Sorry, I have a question. How they keep the steady flow? Okay, so yeah, they don't avoid gravity. Actually, gravity is driving this downwards, right? But what they do is that they take water from the tank below and then just pump it up with a pump with a una bomba. They just put the water back on the top. Okay, so realize that this is steady flow, but you have random fluctuations because the velocity is larger. Okay, and as you can see, if you increase further the velocity, now the ink mixes a lot. It reaches the bottom really well mixed. You can't really see a line. Okay, so this is a neat, I think, example. Here you can see more. This is the same, but you cannot see up the setup of the model. But it's the same idea. So you have very uniform laminar flow, we call. Here we have transition flow because we're increasing the flow rate. And if you increase it further, you get turbulent flow. Okay, and that's the classification that we're going to use. Laminar flow to when the flow is really the water, the fluid is really flowing in layers. So we call it laminar because you have very thin layers moving one on top of the other. And when the flow is more chaotic, it's more random, we're going to call that turbulent flow. Okay. The actual details you don't really need to know, um, but that distinction it is important. So let me switch my camera now. Yes. Can you see my whiteboard? Okay. So we have. Let me just briefly show you. So we said okay. You could have laminar flow and you could have turbulent flow.
Profesor del Rey.
Oh, give me a sec. Now,
Ahí sí.
thank you. Okay, a laminar. In which of these do you think uh, viscosity effect are more important? So recall, viscosity is a property of the fluid that prevents the fluid from deforming, from straining, right? So in which one of these two kind of flows? So laminar flow, I'm just going to draw a very crude uh, laminar flow. It's just like that. So here I'm just injecting ink. A turbulent flow is something like that, right? Which one viscosity you think is more important? No guess?
El laminar.
Laminar flow. Excellent. So in this case, viscosity is important. In this case, viscosity is not. So in this case, you have to use which kind of equations do we use for viscosity, for viscous flows? You recall? Navier-Stokes. Because Navier-Stokes equations include the viscosity. This other one, we can model this by Euler equations, right? Now, somebody is asking, does this depend on the Reynolds numbers? Yes, of course, it does. Probably you've seen that already. So the Reynolds number is defined as as an non-dimensional number, meaning it has no dimensions, and is defined as the ratio between two kind of forces. So it's defined as the ratio between the inertial forces and the viscous forces. Now, what does inertial mean? Inertial is anything that has to do with motion, with with momentum in the end. So it has to do with your own weight and your velocity. Okay, so uh, let me just and normally the Reynolds number, it depends on what kind of flow we're talking about, is how the Reynolds number is defined. So typically the Reynolds number can be defined as the as rho, as the density of the flow, times a typical velocity times a typical length divided by mu, which is the same to say a typical velocity, a typical length divided by nu. If you recall, nu is nothing more than mu over rho. So in a pipe, like we were just showing, u would be the average velocity, and the typical distance will be the diameter of the pipe. This divided by nu. Now you can do a very easy estimate of the value of Reynolds, uh, because let's put a number here. I'm gonna delete this, but just keep it in mind. So first, you can see that this has to be non-dimensional, right? So do you recall the units of nu? Well, the units of velocity are meter per second, and the units of a distance of the diameter are meters. The units of mu, or nu in this case, yeah, I'm gonna get back to why Reynolds is important. Give me 1 second. And the units of nu are meters squared divided by second. You can check it out later on, but that's what it is. So this has no units. It's non-dimensional, right? Now let's make an educated guess of a typical value of the Reynolds number. Do you know the value of nu, right? You can Google it if you don't, but is in the order of 10 to the minus 6, right? I have Wikipedia just in front of me. So kinematic viscosity of water is 10 to the minus 6, yes, something like that. And the velocity that we were just seeing, what do you think it was? It was a meter per second? That's too much? Maybe half a meter per second? So let's say 10 centimeters. So that's 10 to minus 1. And the diameter maybe was, I don't know, less than 10 centimeters too. So 10 to the minus 2. I'm sorry, 10 to the minus 1 again. So this whole thing is something like 10 to the minus 2 divided by 10 to the minus 6. So this is a large number, right? So this is around to 10 to the 4, right? So that's a typical value of the Reynolds number. Now, here's the thing. If we know nu for water, but this number you can use it for any flow, for any fluid. So nu, the viscosity of honey is way higher than this. So the Reynolds number, if the viscosity is high, the Reynolds number is going to be small. On the other hand, if the velocity is very high, then the Reynolds number is going to be higher. So normally, laminar flow occurs for Reynolds number below, let's say, 2000 or something like that. And turbulent flow occurs for flows over 4,000. This is not like a very precise threshold, as you could see, in between those two, you have a transition flow where you have mostly this laminar flow, but then you have random fluctuations. Or you can have almost turbulent flow, but then it kind of gets more order. So the Reynolds number is an indication of which kind of flow we're having. And the cool thing is that the Reynolds number doesn't depend on the fluid. So you can have the same Reynolds number for water or for honey or for any other fluid, and they should fall in the same ranges. So for honey, laminar flow in honey is in the same range of below 2000, and turbulent flow of honey, if that's possible, is in the same range of larger than 4000. Okay, so this number, the Reynolds number, lets you know in which type of flow do you have. Now, this is one way to express it on a pipe, but if you have an open channel, then it's a different way. Okay, um, and it's not very important now, but we can get into that later on. Okay, any question about that?
I have a question.
Yes.
Is this only for circular tubes?
Yeah. No. Actually, that's what I meant. If you have, for instance, if some of you follow the open channel hydraulics, for instance, let's say you have a canal, right? This can be like uh, how do you say, irrigation canal for for crops, or it could be a chipping canal. This could be very large or very small. It doesn't really matter. So if you have a canal, you're normally going to have a height, and you're normally going to have an area. Okay, you don't need to. This is called the wet perimeter. Uh, so no, in this case, in an open canal, the Reynolds number is going to look something like the mean velocity again, but divided by the hydraulic radius, divided by nu, and this is nothing more than the mean velocity times the area divided by the wet perimeter. It doesn't matter. You don't have to remember this, but depending on the geometry of the flow, there are some ways to represent the Reynolds number. Also, if you really get into this later on in life, and you want to model, for instance, how sediment moves, let's say you have a rock or a pebble that's sinking, it's going down. You're gonna have some turbulence around it, you know, and there is a way to represent the Reynolds number of this particle, and it has a specific form. So depending on the type of the flow, is the type of the Reynolds number. That's why and they are all defined more or less to have the same thresholds, but it's not really. They're pretty broad thresholds. So um, yeah. So it on the kind of the flow. If your flow is on a tube on a pipe, then you use the diameter. You can see here that if you use the radius, it won't change much. It's just it's gonna double. But now the difference we're talking about are hundreds of times, thousands of times. So if you double your estimation of the Reynolds number, it doesn't really matter. It's just this should give you like an order of magnitude of what it is. And as the Reynolds number, we're going to see later on, there are other dimensionless numbers that lets us differentiate flow. In this case, we want to differentiate between laminar, where viscosity matters, against turbulent, where viscosity is not really important. Any other questions? You can also see this, if you go to the bathroom and you open the tap. If you open it really just a little bit, you're gonna see a flow that looks like it's solid, right? And if you open it farther, then you're gonna see the turbulent flow going out. So this is something you see. This is something that you can see on your own. So these are the typical regimes that we can find. Uh, I will tell you now that although you don't need to memorize this. Okay, I'm sorry. I'm being asked. Consider the velocity and viscosity of the other fluid with color. What do you mean by that? Um, and Maui, I'm being asked. Consider the velocity and viscosity of the other fluid with color. Okay, maybe I'm a bit lost, but oh yeah. So the ink, you mean the ink that we're putting into the fluid to see the motion? Yeah. So that's a good question. Normally, that tracer or that ink uh, is going to be way more viscous than water, right? So you might do the same calculation in order to determine the the flow regime of the ink. Now, since this is very small and you're only putting like a little tracer, the assumption here is that the tracer is gonna stick to the water molecules and move with it. Okay, so it could be it normally is very viscous. Although here some other things start to take into account, like these things decay. So normally, forgetting the word for it, but normally if you do a field a campaign and you put this kind of ink into a river, after a few hours or maybe a few minutes, the ink will dissipate, will fully uh, will vanish, because otherwise people will complain and all. But yeah, in principle, normally the tracer also you could determine the flow regime for the tracer. Although normally it's more viscous than water. Um, okay. Any other questions? Now this is relevant because it determines which set of equations you have to use. So if viscosity is important, you have to use the Navier-Stokes. If turbulence is important, then you have to use Euler. Although, and this is what I wanted to say before, Euler really is for ideal fluid. Okay, this is fluid that has no friction at all. And in reality, although these equations are pretty useful, in reality you do have some friction. Although small, you do always have some friction. And the way to incorporate that friction is beyond this course. You will see it maybe in the next course on hydraulics, but it has to do with bottom friction and turbulence and how it's called, capa límite in español, boundary layer near the wall. So those are more detailed stuff that we don't need to mind right now. So Euler is for turbulent ideal flow. Navier-Stokes is for real laminar flow. Okay, so try to keep that in mind. Any questions before we move on? Now, what we're gonna do now, I think we're about to enter a break, but before that, let me just introduce what we're gonna do next. Uh, Let me ask you. Maybe you've seen this already, but let me ask you. Let's say you have a blood vessel. Do you know what a blood vessel is? like an artery or a vein, right? Here, blood is flowing. Yeah, a vein or an artery. So you have blood flowing. We've all seen blood. So do you think the flow within a vein or within an artery, it will be turbulent flow or it will be laminar flow? We're gonna call this Q. Laminar, we're being said. Yeah, the flow of blood is pretty laminar, and actually you can use Bernoulli's equation to determine how the blood moves. It's pretty interesting. If you have friends, doctor friends, they can tell you that they study this kind of stuff. So the blood inside a vein is laminar, meaning that viscosity is really important. Blood is really viscous, and the flow within the tube is determined by this viscosity. So what we're going to try to do now is try to derivate equations for a cylindrical tube or a pipe where laminar effects are really important. Uh, and these are normally called Hagen-Poiseuille flow. So let me just write it down. Hagen-Poiseuille. This is Hagen-Poiseuille flow, and it's basically a particular case of the Navier-Stokes equations. So uh, the relevant here is that whenever you want to model laminar flow, you have to start with the Navier-Stokes equations, and then you need to work your way through your particular case. Okay, this is something we did already last week. Recall we had like an infinite plane. We had two plates, right? Infinite plates, one on top of the other, and we had flow here. That's also an example of a Hagen-Poiseuille flow. So this is not a unique thing, but all these two, and also in the recitation, you did something similar, right? But only that you have two fluids with different viscosities. So as you can see, I hope you can see this is a very recurrent thing. So if you want to work with the actual Navier-Stokes equations and you really want to integrate them, you need to have uh, some idealized flow, some idealized cases. Otherwise, they're just impossible to integrate, um, uh, not numerically, but analytically. Okay. So what we're gonna do now is first we're gonna take break of 10 minutes, and then when we come back, we're gonna try to derive the Hagen-Poiseuille equation for laminar flow in a blood vessel. Okay. See you in 10 minutes.
Profesor, tiene el micrófono silenciado, no lo podemos escuchar.
Thank you. I clicked it. Thank you. Okay, what I said is that we're going to try to integrate the Navier-Stokes equation for this particular case of a blood vessel. And these are called one type of Hagen-Poiseuille equations. Okay, so what I said that was critical, I'm sorry you couldn't hear me, is that we're going to use uh, a cylindrical set of coordinates, right? Because a typical blood vessel is pretty much a tubular pipe. So all the flow is going to be, uh, you know, is going to vary with the radius radially. So in this typical cylindrical coordinate system, we're going to have one direction along the flow that we're going to call Z. We're going to have one direction, one radial direction that we're going to call R. And we're going to have a tangential direction, which is normally, let's say this is an equal radius. And we're going to have a tangential direction, which is going to be theta. You've probably seen this in calculus classes or similar, right? This is not really new stuff, and this makes some things easier. Some things it makes a bit harder. Uh, so let me show you. And basically, what we're gonna assume here is that we're gonna have blood flowing in this direction only. Okay, so since this is laminar, we're gonna have layers of blood that will slide along the artery or the vein or whatever with the same velocity. So all along this line, you're gonna have the same velocity. And all along this line, you're gonna have the same velocity, right? So far, that's more or less clear. So uh, there's a new option of using a whiteboard here, but I haven't before. So I'm not gonna improvise. I'm gonna stick with what I had in mind before. But maybe for next class, I'm gonna use the whiteboard of Google Meet. Okay, so now what I'm showing you, or you're about to see, this is just a cheat sheet, let's say, with the Navier-Stokes equations. You know, the Navier-Stokes is basically four equations. One equation for continuity, right? And three equations of momentum that have this vectorial form, right? So very briefly, this is the total derivative that has a local and an advection term. You have the pressure gradient, you have the body force, normally the weight, and you have the viscous forces. And you can express this in each of the three components of the Cartesian uh, system of coordinates. This should be more or less known by now, right? If somebody has any doubt about this, because this should be pretty clear, or if not pretty, almost very clear. Because what we're going to do now is we're going to try to see how this set of equations looks in cylindrical coordinates. Okay, so I'm going to assume this is clear for everyone. Okay, so the first equation is the continuity equation. Okay, in the previous case for Cartesian, we only had the derivatives of each velocity against its own component, right? Now we get this 1 over r in front of the velocities. Okay, I'm not going to go into the details of why do they appear, but it has to do with this, with the Jacobian of the transformation. It doesn't really matter for us, so you can just use it as a given. For incompressible flow, uh, the continuity equation becomes to this one. Okay, and now we have the three Navier-Stokes equations in which you have acceleration, pressure gradient, the body force, and the viscous forces for each three of each three components: the radial one, the tangential one, and here it says Z, but remember the Z is in the direction of the flow. Okay, we're assuming that Z is pointing in the direction of the vein. Okay, so what do we know, since we are using an ideal case of velocity only in the Z component? Uh, can you see my whiteboard? Maybe just very little on a corner, but can you see at least a fraction of it? Because I want to show you a very uh, I want to show you how to select the terms that are relevant from the Navier-Stokes equations, and then we're gonna do the math on the whiteboard. But it's easier if I just show you here instead of copying all the full equations. But uh, what what we're assuming, maybe you can see it here, is that the velocity and realize that here we're calling velocities u r and u theta and u z. So these are the velocities along the radius, um, along the tangential direction, and along the vein. And we're assuming only the velocity along the vein is non-zero. So we're assuming u r is equal to u theta, and those are zero, and those are always zero. Okay. Also, we want to solve a steady flow, because adding time on top of of everything just makes everything more complicated. So steady flow means every derivative against time is also zero. Okay. With that in mind, we can start discarding terms. So what we can discard right away, if u r is zero, then any derivative of it is zero, right? So the first term of the continuity equation is zero, and the same goes for u theta. There is no flow tangential to the cross section, so this is also zero. Oh, this is also zero. So we end up with I'm gonna write it down here and then we'll come back. So the continuity equation says that derivative of u z over z is zero. That means that even though we have a value for u z, which in turn might depend on the other variables, uh, this value doesn't change over z. So it doesn't matter which section we cut, in which section we evaluate this. If the section doesn't change, then u z has to be, the velocity in z has to be constant. We don't know the value yet, but it has to be constant. Is that clear, or am I going too fast? Okay. So from the continuity equation, we only get this bit. Oh, again. For the continuity equation, we get this bit only. Okay, let's look at the radial component. We said that this is not changing over time. This is steady flow. So this term on the acceleration, do recall this is the local acceleration. We're gonna say this is zero, and all of these terms here are the advective acceleration. Again, you can see this u theta over r, and here you see this u theta square over r. This is the radial acceleration. Don't mind about where do these term come, because in this case this is just a given. This is a calculus derivation that we're not pretty interested in right now. What we do know is that we said ur is zero, therefore it doesn't change over the radius either. So this guy is zero. Also, you see ur is zero, so we could have just eliminated because of that. and u theta also 0, so this is 0. But also the derivative of ur with respect to theta is also 0. So these guys are 0 for all those reasons. The same goes with this. The velocity, the tangential velocity is 0, is not changing. uz is not 0. We know that because it's actually what we want to compute. But ur is 0. So the derivative with respect to z of ur is also 0. So you see, what we're saying here is that this whole acceleration term is 0, which makes perfect sense because we are evaluating steady flow over a tube that doesn't change in shape, right? So it makes sense that there is no acceleration in this case. I'm going to repeat that. Realize that there is no acceleration in R, and that makes perfect sense. If it doesn't make sense to you, try to realize why, but it makes perfect sense that we have no acceleration because this is steady flow and we have no change on the geometry. If it doesn't make sense, you can ask questions, but I think this is a key thing to realize. Uh, moving on with the momentum equation in R, we have the rate the gradient of pressure over R. This we don't really know what it is, so we can't eliminate. Here we have the body force over R, which is most likely not 0. We have these terms. Okay, let's have a look at them. Again, we have this derivative of UR has to be 0. Here we have UR, which we know it's 0. Derivative of UR, which is 0. Derivative of U theta, which is 0. And derivative of UR. So all the terms due to viscosity of the R component are 0 because we have no motion in the R direction. Again, the R direction is the radial direction from the center of the vein to the wall. And we have no motion in that direction, so we have no viscosity effect on that direction. That also should be pretty clear. So we're going to come back to this later, but the momentum equation on R, I'm gonna I'm writing down in the whiteboard, and I will come back later. But this is just the clean version of the equation. So we have the 0 acceleration is it has to be equal to minus the gradient of pressure with respect to R plus rho gr. Okay, let's do the same for the theta. Any questions so far? Is this too confusing? Is this too simple? Any comment? Okay, moving on. We know for the theta component, we know that this is steady flow, so this derivative is 0. We know that ur is 0. We know that u theta is 0, the same as before, so this guy is also 0. uz is not 0, but the derivative of u theta with respect to anything is 0 because u theta is 0. So again, no acceleration in the tangential direction, which again makes perfect sense. If it doesn't make sense to you, try to have a look. And now we have the derivative with respect to of the pressure with respect to theta, but with this radius 1 over radius before. Again, this has to do with the way the system is expressed. Don't bother about that because you're just given this equation. And then we have the body force of G, right, in the theta direction. And now we have these second order derivatives that express the viscous effect, right? The same as before, the derivative of u theta with respect to r is 0. U theta is 0. This derivative is also 0. This is 0. This is 0. So no viscous effect on the tangential direction. And what we get again is that 0 is equal to minus 1 r, the derivative of pressure with respect to theta, plus rho g theta. Great. So pretty similar than before. And the z component, which is the key one. Again, you could, you could say beforehand that there's not going to be acceleration, but it makes sense physically. But you can actually check it. So again, no derivative with respect to time. You said, oh, I'm sorry. I said I made a mistake. So there is going to be acceleration or not? No. I'm sorry. There's not going to be acceleration. So let's go one by one. This guy is 0. The velocity of u z with respect to r is, this is not 0 because actually it's going to change, but it's multiplied by u r. So this term is 0 too. Uh, this term is 0, but also the velocity won't change with theta. Doesn't matter. We're saying that the flow is going to have a radial behavior. So this guy is 0 too. Just to make it clear, this guy is not 0, but this guy is. So we can cancel it. And again, this is not 0, but this is because of the continuity equation. So as foreseen, no acceleration. That makes sense. And now we have the pressure gradient along the vein or along Z. We have the body force along Z, and we have the viscous forces. Now, uh, let's go. Let's go here. We know that the derivative of uz with respect to z is 0. Therefore, the second derivative is also 0. So this guy is 0. We already said that this is not going to change over the radius, so this is 0. And this we can't really eliminate because we don't know how the velocity is going to change with respect to the radius. So these terms remain. Okay, so the momentum equation with respect to z remains as 0 equals minus dp at dz plus mu times 1 over r times the derivative with respect to r of r and the derivative of uz with respect to r. Right? Is this clear, or do you have any questions before I move to the whiteboard? Okay, so basically we just remain with this, this, and this. Okay, back to the whiteboard. So I'm going to delete this. Not yet, not yet, because it is important. Now, before we move on, we have here, I'm sorry, and here I forgot plus rho gz. Okay. So before we move on, we need to address these body forces. Now, we know that G is acting vertically downward. So this is G. Now, you can always think of G as a vector. And let's say that we impose a Cartesian system of coordinates here. So if we put a Cartesian system here, we're going to have, this is going to be x, this is going to be y, this angle is going to be theta, right? So g is going to be minus g, the value, in the unit vector of y, right? And you might recall from your trigonometry classes, r vector is going to be cosine of theta in I, in the x direction, plus sine of theta on j, and the theta unit vector, which is this one, is going to be uh, minus sine of theta in I plus cosine theta in j. Why I'm doing this? Because you can see as we move the point that we're interested, let's say at some point we're going to be interested in this point, then this guy is going to be r, and this guy is going to be theta. And we need to determine how g is going to be projected into each of these directions, because that's what's going to give us these three values. Now, I'm going to delete here just to have a little space. You should be able to see right away that gz has to be 0 if this vein is horizontal. So if this is horizontal, then this is 0. And gr and g theta are nothing more. Gr is nothing more than g, the vector, dot product, the r vector, unit vector. So here we're going to get minus g sine of theta. And g theta, same thing, times, and this is going to give us minus g cosine of theta. Okay? Is this clear or not? I know this can be a bit confusing, but again, what we're doing here is try to determine how the weight of the fluid is going to be distributed over these cylindrical coordinates. And this is, and therefore, the body accelerations in each direction are going to be this. So I'm going to delete this, and I hope the scheme is pretty clear because I'm going to delete it too. Okay, now that we have that, we can go and try to integrate this. So let me keep this here. Let me try to integrate it. So we could say we have the p at the r is equal to minus rho g sine of theta. Okay, that this is replacing this value here, right? Therefore, if we integrate this, we're going to have the, I can do this, I can take the time a bit. So this dp minus rho g sine of theta dr. And if we integrate this, we get p is minus rho g r sine of theta plus a certain constant, right? And I'm going to call this constant P0, some reference pressure, right? Now, what you can see, r sinus of theta, this is nothing more than the vertical direction, right? This is r, this is theta, so this is r sinus theta. So what this is saying us is that pressure is going to be some reference pressure, P0, and then it's going to drop as we go up. So this is, again, this is hydrostatics. Now the question is, what is P0? Is this clear? Or is this too cryptic? Okay, from the other side, we have, if we take the equation on theta, I'm gonna write this in other color just to make it look different. If we use this in theta, we're gonna have uh, dp over d theta equals, I'm gonna move this r to the other side, rho g r cosine theta. Okay, so the pressure changes along the tangential direction, not on the sine, but on the cosine. And we can use this equation to try to determine this P0. Okay, in principle, P0, well, we don't know that value, so let's leave it that way. Okay, so what we can do is that we can take this expression for P and derivate it against theta. Okay, so I'm sorry for the mess. This is a rather small blackboard, but I'm going to take this equation, I'm going to derive it against theta. So the P at the theta is going to be this value here, which is constant. So rho g r. And cosine theta is, I mean, sine, the derivative of sine is cosine. So cosine theta plus dp0 at the theta, right? Now you can see from this equation uh, that this equation is just the same as this. So that means that that this final bit, the derivative of p0 with respect to theta, has to be zero. It has to be zero. That doesn't mean that p0 is zero at all. It doesn't mean that. It means that it doesn't change with theta. Okay, so p0 only depends. P0 is a function of z. Only depends on the position along the tube, right? Can't depend on r because we already integrated on r. So p0 is a integration constant on r, and it doesn't depend on theta. So it has to only depend on z. Okay, and p0, it can't be, for instance, the pressure at the center line of the vein, or the mean pressure, and it will only change along z direction, along the vein. Okay, and these two equations say, okay, inside the vein we have hydrostatic pressure, and pressure increases as you move down the vein. Of course, the vein is very small, so this is not very important, but this is what it says. So and it makes it checks out with what we know. Okay, so that's what we get from these two equations. Okay, so we have hydrostatic pressure, and the reference pressure depends only on z. P0 depends on z, and we have hydrostatic pressure. Hydrostatic. Okay, now comes the fun part, I guess. We're going to try to integrate the third equation to determine the velocity profile. Okay, I didn't understand the last part. Can you repeat it, please? Yes, I can. I wish I read that before I deleted this, but basically, from the two momentum equations on r and on theta, we have now this. We have that the pressure changes with this equation, and this is r times sinus of theta. This is just y. This is the vertical direction. So the pressure decreases as you move up, and you need a reference value, some p0, which is an integration constant, right? But we also have this other equation of how the pressure changes on the tangential direction. Now, if you derive p, which we know p is this expression, if you derive this expression with respect to theta, you get exactly this expression. You get, the derivative of sinus of theta is cosine of theta, so you get the same expression. Therefore, if you derive this with respect to theta, you get that the derivative of p0 with respect to theta has to be 0. It's the only way that this expression, the blue one, becomes the green one once you derive with theta, with respect to theta. And if p0 or any number doesn't, if the derivative with respect to theta is 0, means that p0 doesn't change with theta. So if we look into the vein, if you're here, you're going to have a certain p0. If you're all along, you're going to have a certain p0. Now, p0 doesn't change on R either because we integrated here. So any section of the vein is going to have the same p0, which is again a reference pressure. Normally, it's going to be the pressure at the center, but it's a reference pressure. It doesn't really matter the value. What we know is that uh, we know that p0 has to be only a function of z, which is the only variable we haven't used yet. So it has to be a function of z. This is not very, very important right now, but it might help you to understand what I'm going to say later. So if it wasn't clear enough, maybe I just repeated myself. But if it wasn't clear enough, just put a pin on that thought, and I'll try to come back in a few steps. Okay. Any question before I move on? I think okay. Hopefully it will be clearer. Just give me a few minutes, and maybe you'll see. Maybe you won't. I don't know, but hopefully I'm going to try to make it clear. Okay, so now we're going to try to integrate this equation. This equation. So let me just write it back again. Uh, Again, it's clear that g z is 0, right? So I'm not going to write that. So what we have is that let me rearrange this. Let me just okay. Let me just write it from the beginning, and then we can rearrange. So the derivative of pressure with respect to z plus, I'm gonna just delete this, all right? Plus, so this is 0, so I'm gonna just mu over r, derivative with respect to r of r, the derivative of, I'm just gonna use u, okay? It's u z actually, but I'm gonna use just u because that's the only value. So I don't have that many lines. Okay, so we have this. So again, u is the velocity normal to a cross section, and we're interested in determining how u changes over r. So our main goal is to determine u over r. This is the function that we're looking for. So what we're gonna do is that we're gonna simplify this and we're gonna integrate. So let me move this to this side. So we get dp over dz, and I can multiply this by r and divide by mu. And this has to be the same as d at dr of r du dr, right? That shouldn't be too scary. Now we're going to integrate this with respect to dr. And here we're going to get 1 over 2 mu dp dz times r squared plus a certain constant, right? And here we're gonna get, on the other side, we're gonna get r. Basically, we cancel out this derivative, r times du at dr, right? Now this r, I can pass it here. So I'm gonna do whiteboard math. Hopefully you can follow along. And now I'm gonna integrate again with respect to dr. So what I get here is another 2. So it's going to be 4 dp dz r squared times this derivative. Do you have it uh, to recall it? The derivative of 1 over r. Okay, this is a natural logarithm of r plus another constant, and this is u. Okay, so this is expression for u. Yes? Is it clear? Now, what do we know? Again, I'm looking at the vein just in front. We know that here at the center we're going to have a certain velocity, and here at the wall we're going to have another velocity. The velocity at the wall has to be 0, right? Remember, we have this no slip condition. So when r is big R, we're going to call the radius of this r. The velocity at the boundary has to be 0, and the velocity on the center, we're going to call this. Let me call this u naught. U naught is a certain value. Okay. So let me evaluate u when r is 0. Well, when r is 0, we have this is 0 plus c. Do you know the logarithmic of 0? Plus c2. Do you know it? This is plus infinite. Actually, the logarithmic is not well defined in 0. And this doesn't make sense, right? It's not that I made a mistake. I didn't. But this is just to tell you, okay, c1 has to be 0 because the velocity has to be finite. Therefore, c2 is the velocity at the center, at the center of the pipe. When r is 0, we have z2. Is that clear? So we're gonna call c2. We're gonna call this u naught. Okay. So the velocity at the center is u naught. Now, what's the value of u naught? Well, we can evaluate that. We know the u when r is big R uh, has to be 0. That means that maybe I'm a bit corner here, but 1 over 4 mu dp dz times big R square plus u naught. This has to be 0. So from here, u naught has to be minus this chunk, right? Minus 1 over 4 mu dp dz r square. Okay, and with that, we can really, I'm going to delete this. With that, we can really get, oh, maybe I shouldn't have, sorry. But maybe with that, we can get like a final version of the velocity. So u of r is really, I'm sorry, I shouldn't have deleted that, I'm sorry. But u of r is, well, it's really here, right? It's 1 over 4 mu dp dz times r squared minus r square, big R square. Now, what do you see here? Do you see anything funny? When this is 0, uh, you get u0. I mean, when this is r squared, this is 0, so you get 0. That's fine. And when this is 0, you have minus r, and then you have this value. what you can infer from here, and this is very similar to what we did last week, is that this guy has to be negative. So the pressure along Z, it's dropping, it's decreasing. Remember we said P0 depends only on Z? Well, beside P0, you also have a vertical variation of pressure, right? But the P0, this reference value, changes along Z, and it's actually decreasing. And that, again, makes sense. If you have a horizontal blood vessel or pipe or whatever, here you have the same energy than here. You have the same Z. You have the same velocity. So v squared to g they are the same. The only thing that you can do to make the fluid flow is that P1 be larger than P2. If the energy here is larger than here, then the fluid is going to flow in that direction. So dP at dz, we don't know this value in this case, but this is the driver of the flow. Okay. And well, since is that clear? I think I made the same point last week, but I think it's important. So if it's not clear, I can spend another minute here. And realize that u0 also has this negative value. So this has to be negative because so far we haven't seen any directions. We're just talking about magnitude. So this has to be positive. So this has to be negative. Okay. And we can input this, factoring this into our description. So let me just delete this and this. Hey, I'm sorry, my internet dropped. I don't know how long you lost or for how long I've been talking alone. But did you see this? Did you see this? This pressure gradient has to be negative. All right, great. So basically, the velocity can be expressed as this one. So we have a center velocity. So when the radius is 0, you get this. When the radius is big R, you get 0. So this is the expression. And now what we can do is a typical question, and I said this last week, and I'm saying it again. Typical question is compute the average velocity. All right. So and also you could plot this, right? I mean, let's say you have your vein here. How would this look? This will be something like uh this would be something like that, right? Like a quadratic stuff. So here you're gonna have u naught, here you're gonna have u equals 0, and it's gonna be some parabola, right? And now we're interested in, okay, but what's the average velocity, mean velocity? Yeah, I'm being asked, is that the Hagen-Poiseuille equation? Yeah, well, it depends. I mean, you can look at the entry on Wikipedia, and there they use the Hagen-Poiseuille equation. They use it to determine the flow. The flow. Let me write this. The flow Q as a function of the pressure drop over a distance, which is the same as or very similar to this. And you get this equation, and that's the equation of Hagen-Poiseuille, and you get this equation uh, by integrating u of r over the area. If you integrate the velocity over the area, uh, you get the total flow. Okay, and this is going to be a function of dp at dz, which is pretty similar to delta p over L. So you can look it on there. Um, but yeah, but that's the equation. So the question is, what's the final equation? Well, it will depend on what you're being asked. All right. So normally we will ask you to determine, for instance, now what's the velocity profile? This is the velocity profile. Of course, you don't need to express it as you know. You can express it as these values you got. I mean, this is also a good expression. This is also a good expression. Normally, you're also being asked, okay, what's the average velocity? So determine the mean velocity, or determine the flow. Okay, and the flow is this, is the integration of this. So, and also the flow is also the average velocity times the area. So if you do one of those, you can do the other, right? So okay, if I answer your question, the Hagen-Poiseuille equation relates the flow with the pressure drop. Okay, uh, and test related stuff. Okay, we're being asked, how do I get the gradient in pressure? That's a very good question, but we're not gonna mind ourselves now. But that's a typical problem, because normally, so far we're assuming this guy is constant, but it doesn't really have to be constant. Okay, so you don't need to remember this, but since you're asking, all of this development assume that zeta one z1 is equal to z2, like horizontal pipe, right? By continuity, v1 has to be equal to v2. It has to be equal, okay, because the area is not changing. So the only thing dropping is the pressure. Now, if you remember, the the Boussinesq here has to be the same as the Boussinesq here, right? But when did we do this? When could we say that the Boussinesq was conserved? What do you mean in English, Matthias? B1. I'm sorry. The Bernoulli. Yeah. Sorry. The Bernoulli. Yeah, this is the Bernoulli. Boussinesq is another is another famous hydraulics. I just got them confused. Yeah, this is the Bernoulli. I'm sorry. So the Bernoulli here has to be the same as the Bernoulli here, right? Um, and the Bernoulli, we said, the Bernoulli on the point I is just the position plus the pressure divided by gamma plus V1 VI squared 2G. Do you recall this? This is quite important, eh? So we're saying, well, C doesn't change, V doesn't change, only P can change along the pipe. But we used to say, okay, we can assume the Bernoulli to be constant, right? So in which case we could say that the Bernoullian one was equal to the Bernoullian 2. Do you recall? If you don't recall, let's have a look. But the Bernoulli is basically the Euler equation integrated over a streamline. So basically, we're assuming, okay, we have a streamline here, and we're integrating Euler equation. But we know that we're solving the Navier-Stokes equation. So Euler can't describe right this flow. So what's happening here is that the viscosity, the friction, it's reducing the energy. So the Bernoulli is a measure of the energy of the flow. So in this case, these are not equal, but B1 is actually larger than B2. Okay. And therefore, and that's because P1 has to be larger than P2. And this gradient, dP over dZ, is due to friction. So friction is the main cause of why pressure is dropping. Okay. And there are ways to compute this pressure, this drop in energy because of friction, that we're not going to go into details now, but we could compute how the pressure is dropping because of the friction. And this is where it gets complicated because uh, this, as you can imagine, this depends on the velocity. So the larger the velocity, the larger the pressure drop. So it's not easy to integrate. Okay. So for all practical matters, we can assume this is a constant and it's just given. Okay, we could compute it, but that's beyond the scope of what we're doing here. You should know, though, that this change in pressure is due to viscosity. And since we have viscosity, we cannot use the Euler equation. And that's why the Bernoulli at this point is larger than the Bernoulli along the line. Is that clear? Does it make sense? We're mixing concepts from the previous unit into this unit. And I think it's a very, very, very good question, because otherwise you're just repeating formula. Okay, this is the physical meaning behind it. Is that clear? Okay, and as a side note, I said Boussinesq. You can look it up. Boussinesq was a French guy, and basically his equations describe waves, like when you want to surf a wave. So I got them mixed up, but it's not important. I meant to say Bernoulli here. Okay, um, that was the main idea. I wanted to do this integration, uh, but taking into account what we said last week, I mean, this is the main thing. The flow is going to be the average velocity times the area, and the average velocity let me just the average velocity is just going to be the area over the integral of u of r dA. So you can compute q directly, or you can compute the average velocity and then multiply. Is this clear? This bit, despite the details of how we could do it in this particular case, but this should be more or less clear. I mean, this is the average velocity. The flow is just the integration of the velocity over the area. This is the general. Let me just drop this. This is the general case. So you could use this in any problem once you solve the velocity profile. So I'm going to ask you: do you want us to go ahead and do this integration, or we can call it a day and you can do it later on. I don't mind, but since we can maybe finish a bit early, if you like. Okay, I'm gonna leave this to you. Maybe try to do it in your house, but since you have the velocity profile, try to determine the mean velocity and try to determine the flow, the actual flow. Uh, if you're able to do this, then you're in a very good position for the yeah integrated. Yes, yeah, this integration. You should be able to do this on a test, for example. You did this on the past recitation. We did it on the past class, and I can do it now if you want, or we can just finish now and you can do it later on. Well, I'm being asked if it's too long. It depends. I think it's pretty straightforward, but no, I think it's short. 10 minutes, 15 minutes. All right, let's do it. Okay, so a typical question is going to be to determine the mean velocity profile. So we're going to do just that. Uh, and like I said, I'm going to do it here. But like I said, I'm going to just repeat myself. The mean velocity profile is just 1 over the area, the integral of u over the area. This is like definition of weighted average, right? We've seen this already with pressures, remember? This is a weighted average. Okay, so what is the area? It's just p pi r squared, right? And what's the delta area? That's a bit tricky, but it's not super tricky. Let's again look at this vein, and let's assume we know that the velocity only changes with radius. So let's say we take a radius. Okay, this is awful, but try to picture it. So if we take a radius, this is a delta area in which the velocity you have the same velocity. This delta area is r times 2pr dr, right? You should be able to see this.
I can't. Is that formula okay?
I would say so.
Isn't it minus something? Because it is like a ring. It's not a circumference.
Yeah, let's start smaller. Let's say we only take this bit. Okay, this is we know the a is r dr d theta. We know this, right?
Yes, yes.
Okay, because this side here is r d theta, and this side here is the I'm sorry, this is dr. So this is the delta area. Now, what I'm saying is you can also integrate it like that. So let me just this were clear, right? So I'm gonna keep on using the green. So u average is 1 over p r square, and then we have the integration, and we can integrate. Here I'm integrating over the area, but you can be more precise, and actually you're integrating over the radius between 0 and r, and over theta between 0 and 2p. Okay, so so far we're just going to use that for the moment. Then the area, which we said here's r dr d theta. So this is right too, but you need to do a double integral, which is fine. If you can do it, is fine. So let me just show you that since this guy, the velocity doesn't depend on theta, we can actually separate this. So it's 1 p r squared, the integral between 0 and 2p of the theta, and the integral between 0 and r of ur times r dr, right? And this guy here is 2p. That's what I meant here. Here uh you have 2p, here you have r. Okay, I had an extra r. That's right. So it's 2p r dr. You see, this is 2p r dr times the velocity. So the delta area is 2p r dr. Right. I had an extra r before. Excellent. Now that we are here, we can just continue. So I said this is 2p, so I'm just going to put the 2 r square, the integral of 0 between r 0 and r of this guy, u0 1 minus r times r dr. Is everyone following now? I'm going to assume you are. Excellent. Well, u0, we can take it out too. Just remember u0 is just this, right? It's just this times this minus, right? So it doesn't matter. It's just a constant that I'm clumping everything together. So we can take u0 out. So this is 2u0 r square times the following. We have the integral between 0 and r of r, because I'm multiplying this, plus dr, I'm sorry, plus the integral between 0 and r of r cubed, right? Divided over r squared dr. Excellent. And this is 2u0 r squared plus, this is r squared half, right? Evaluated only on big R. So r squared half. I'm sorry, this is minus. Minus come here. Minus, this is r to the fourth power divided by 4, evaluated in big R. So r to the power 4 divided by 4 uh, divided by r, right? So I'm gonna do this again, right? This is this is 2u0 r square. You can see here that here is 4 squared minus 2, so it's 2r squared divided by 8, right? And I'm gonna delete this part. I'm gonna keep that because it's actually interesting. So u mean is, well, we can kill this out. This is 4, so it's actually pretty cool. It's u0 half. So the average velocity is just half of the maximum velocity, which is the velocity at the center. Okay. This could not be u0, it could be, minus 1 over mu, whatever, half. So you end up minus 1/8 mu dp dz, I think, r squared, which is what you get on Wikipedia. If you want to go and check it, this is what you get in Wikipedia. So this is right. But the interesting part is that the average velocity is just half of the maximum velocity, which is not at all obvious, because this is like we showed before. This is a quadratic formula. So here you have u0, and here you have 0. And oddly enough, the average is just u0 half. Okay. This is not always the case, but it is the case now. And again, I'm gonna just delete this part. If you were asked to compute the actual flow, well, the flow is nothing more than u half times the area. So u0 half times b r squared. This would be the flow, right? You could have integrated the flow directly and then obtain the mean velocity. But yeah, as long as I do realize that the physics makes sense, and it's actually pretty simple once you understand what you're doing, but it can be very, very easy to get lost into the math, right? And integrate wrongly, and forget a certain constant or whatever, or forget that you know uh, do an integration wrong. So you need to keep uh, your eyes open. I mean, this can be very confusing, but the physics should be sound. I mean, the velocity has to be a fraction of the maximum velocity. That makes sense. If you get, I don't know, 10 times u0, then it's wrong. It's clearly wrong, right? So try to do that kind of sanity checks if you can, of course. Also, yeah, a little step, like a little mistake like the one I was about to make here with this wrong r at the beginning. Uh, it would have given me a really nasty and wrong result. So you need to be careful with with the details. Like, you need to know how to express these differential areas. You need to know how to integrate simple common functions, and you need to try to make sense of the physical values that you're seeing. Okay, so that was it for today. Uh, so let me just wrap it real quick. We finished unit 4, which has to do with differential analysis, in which basically what we did was to try to expand the Navier-Stokes equations and how to use them. We also, let me just increase the resolution here. We also finished unit 3, which had to do with flow patterns, and the formal name is yeah, the kinematics, right? The velocities, how velocities are described. And then unit 4 has to do with how we represent those velocities with the Euler equation, which was only valid for ideal fluids. Then the Navier-Stokes equations, which are valid for actual fluids, for real fluids with viscosity, which are valid only when viscosity is important. If viscosity is not important, then Euler equations are a better approximation. And then we can use this constant Bernoulli approach, which is just integrate the Euler equations along one streamline of fluid. Okay, just to reiterate, we're gonna have a quiz on these 2 units next Monday. So I'm probably gonna post it on Friday, so you have time to read again those 2 chapters, and have time to answer the quiz. Should be relatively easy, like most quiz have been. Yeah, so that could be. And if you have questions, we can have a little, I don't know, 10, 5 minute questions now in Spanish, if you'd like. Cualquier pregunta que quieran hacer, si la quieren hacer en español, ahora, igual como tuvimos al principio de la clase, este es un buen momento para hacerlas.
Profe, con respecto al control,
Sí,
¿van a entrar las 2 unidades completas para el
Sí.
control? Ah, ya.
sí.
Ya.
Probablemente, como han sido siempre los quizzes, no es necesario, o sea, no les vamos a preguntar este tipo de integración para nada. ¿Ya? Debiera ser, el quiz debiera tomarles 10 minutos. Entonces, con tal que se hayan leído la materia y la entiendan, debiera ser suficiente. Hasta ahora los 2 o 3 quiz que ya llevamos les ha ido bien, así que eh, solo revisen la materia. Hay materia que no hemos evaluado, entonces para que no se nos pase más el tiempo, vamos a evaluar esto este próximo lunes. Eh, no creo que hagamos muchas más tareas, probablemente una más, en línea con lo que hablamos la semana pasada. Así que sí vamos a mantener el tema este de los quizzes. ¿Ya? Eso. ¿Alguna otra pregunta administrativa o de materia?
Sí, yo tengo una de lo que
Sí,
vimos hoy día,
sí.
que si me pudiera explicar con un poco más arcaico el tema de por qué la presión varía a lo largo del eje Z. Como que eso no me quedo, no lo puedo imaginar.
Ya. Eh,
Porque o sea, como que, según lo que vimos a principio del semestre, como que a lo largo del eje, como el eje XY, debería variar presión.
eso es cuando mira, es bueno el comentario. Cuando el flujo es hidrostático, no hay cambio de presión horizontal. Eso lo vimos al principio.
Entonces este cambio, bueno, de lo que vimos hoy día vendría siendo por la velocidad al final.
Exacto. Como hay velocidad, la viscosidad es importante. Y como hay un flujo de un lado a otro, la velocidad lo que hace es que va eliminando energía. Imagínate un flujo horizontal en una tubería horizontal. Como hay velocidad, hay deformación lateral y por lo tanto la viscosidad está actuando. Y la viscosidad va disipando energía. Igual que, qué sé yo, si tú tiras una caja sobre el suelo, va a ir derrapando y va a ir disipando energía hasta que la caja se va a detener. Lo mismo un fluido que fluye en una tubería, la viscosidad va quitando la energía. Por lo tanto, y la energía en un fluido nosotros la medimos como eh, cota, eh, velocity head o altura de velocidad y una altura de presión. ¿Cierto? La medimos como una altura de energía, como un head. Si la velocidad es la misma y la cota es la misma, lo único que puede ir bajando es la presión. ¿Ya? Entonces, lo que hace la viscosidad es que va disipando energía y esa disipación solo la vemos en la presión. ¿Ya? Por eso les decía, en este caso podemos considerar que esta derivada de P a de Z es constante para todo para lo que nos interesa es constante, pero en realidad depende también del mismo flujo, ¿ya? Y la forma en que depende no es obvia, ¿ya? Eso es un problema que va más allá de este curso, que a lo mejor tiene que ver mucho más con turbulencia, pero lo mismo, pero hay formas de relacionar esa pérdida de energía, que es una pérdida de presión, que es un gradiente de presión, con las características de la velocidad, con la velocidad y la fricción, ¿ya? Pero eso no nos va a interesar. Solo tienes que mantener en la cabeza que la presión va bajando porque hay fricción y hay fricción porque hay viscosidad. ¿Ya? Eso es lo relevante. No sé si ahí queda más claro.
Sí, me quedó claro. Gracias, profe.
Perfecto. Me preguntan, ¿solo van a hacer 3 notas de las tareas o se van a mezclar con los quizzes? Las tareas y los quizzes, cada uno pesa 5% del curso. ¿Ya? Entonces son por separado. Hasta ahora llevamos 2 tareas y la tarea 2 mucha gente no la entregó. Por lo tanto, seguro vamos a hacer al menos una tarea más. ¿Ya? A mí me interesa que puedan subir esa nota. Eh, ahora, en la tarea 1 les fue bien. La tarea 2 solamente les fue un poquito más mal. Así que yo creo que vamos a hacer solo una tarea más, porque es mucho esfuerzo para solo un 5%. En cambio, en los quizzes, yo creo que probablemente va a ser o toda la semana o semana por medio. ¿Ya? Quizzes vamos a hacer varios más. Al menos, al menos uno por cada tema que nos queda. ¿Ya? O sea, al menos queda el del lunes y 2 más, más una tarea. Quizás si es que avanzamos bien y alcanzamos a ver la última unidad que tiene que ver con turbulencia, de hecho tiene que ver con esto mismo que estamos hablando, eh, quizás hacemos una tarea más por ahí. ¿Ya? Pero hasta ahora van a ser 3 tareas. Y no se mezclan, cada uno va 5% por separado. Ya preguntan, ¿siempre la presión va bajando? No siempre, ¿ya? Pero siempre, igual que en cualquier sistema físico, siempre la energía va bajando. A lo largo del flujo, siempre la energía total tiene que ir bajando. Puede que en alguna parte, no sé, disminuye mucho la velocidad y la presión aumente para mantener las cosas constantes. O, como pasa alguna vez, no sé si han visto las descargas de las represas, que tienen un salto, ¿cierto? Un rápido descarga. Ahí el agua fluye con tanta velocidad que la presión baja tanto que de hecho llega a ser negativa. ¿Ya? Pero una vez que el agua salta y entra al río que está abajo, lo que sea, la presión vuelve a subir. Por lo tanto, no es que la presión vaya bajando siempre, pero sí, para que haya un flujo de un punto a otro, en el primer punto tiene que haber más energía que en el segundo. ¿Ya? Y normalmente lo que hemos hecho en los 2 ejemplos que hemos visto es que esta tubería o esta geometría por donde va fluyendo este flujo está horizontal y la geometría no cambia. Si está horizontal, la cota es la misma y si la geometría no cambia, las velocidades son las mismas. Por lo tanto, el único componente de energía que nos queda es la presión. Por eso la presión va bajando, ¿ya? Pero, por ejemplo, si fuera pintura deslizando sobre una pared vertical, ¿ya? Una capa de pintura deslizando, ¿ya? Y tú le estás chorreando pintura, tú estás agregando pintura y esto va deslizando. Toda esa pintura está a presión atmosférica todo el tiempo. Y ahí el driver, lo que está moviendo el flujo, es de hecho su peso propio, es su gravedad. Entonces tienes igual una disminución en energía, porque vas bajando en posición, pero de hecho la presión no va cambiando al interior del flujo, ¿ya? Entonces no es que siempre la presión baje, pero la energía total tiene que ir bajando, ¿ya? En un río, en cualquier flujo, en un glaciar, lo que sea, siempre el flujo va en una dirección donde hay un descenso de la energía total. ¿Se entiende, Roberto? Perfecto. Me preguntan si es que podemos hacer una alternativa a las tareas de programación. Esto lo hablamos la vez pasada. Va a haber una tarea más de programación, eso es seguro. Eso no hay opción de que lo cambiemos, ¿ya? Porque a mí me interesa que aprendan a programar algunas cosas y necesito que vean que muchos de los problemas que tenemos acá, si tratamos de resolverlo analíticamente, a veces es más complicado que si tratamos de resolver numéricamente, ¿ya? Al menos esa fue mi idea en la última tarea, pero claro, se complicaron las cosas quizá un poco más. Así que va a haber una tarea de programación más. Todavía no sé cuándo, todavía no sé de qué. Sí está la posibilidad, pero tampoco lo tengo tan claro, de aquí al final del curso, de hacer tareas tipo bonus, ¿ya? Que pueden ser una tarea de desarrollo, pueden ser, no lo tengo claro. Y va a depender de cómo nos vaya en las tareas y en los quizzes de aquí en adelante y cómo les vaya en la siguiente prueba. En el midterm 1, tampoco es que les fue tan mal, pero digamos que más o menos la mitad del curso estuvo por debajo del 4, pero no hubo ningún 1, ¿cachai? O sea, hubo muchos que estaban, no sé, un 3.8, un 3.7, lo que no es terrible. Entonces, y de hecho la primera prueba es la que pesa menos dentro del curso, ¿ya? Las que pesan más son las que vienen y las siguientes. Por lo tanto, después de la segunda prueba, vamos a ver, vamos a tomarle más el pulso a cómo vamos y vamos a permitir dar tareas o algunas alternativas para que puedan generar puntos de más, ¿ya?
Es
Pero no
que, o
vamos a
sea,
reemplazar.
esa hice yo la pregunta porque igual la tarea de programación, si bien era programar, por lo menos estaba cachando un poco mejor la materia.
Sí, 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 sí. Mira, las tareas de programación, el objetivo de todo, mi objetivo es que ustedes aprendan esta cuestión, ¿ya? Yo no soy profesor, yo no soy académico, yo no publico paper, así que mi objetivo es que ustedes aprendan. Ojalá también que les guste el curso y ojalá que aprendan herramientas para el día de mañana, si es que ustedes quieren seguir asociados con la hidráulica, sean herramientas útiles. Eso es lo que yo quiero, ¿ya? Y yo estoy convencido que programar es muy, muy importante en hidráulica. Así que yo tomo mi parte de responsabilidad, quizá la última tarea yo la planteé mal, quizás se podría haber hecho de otra manera, no sé, pero de que queda al menos una tarea donde va a haber que programar al menos algo, eso va a ser así. Voy a tratar, o sea, en ningún caso va a ser tan larga como la última, ni tan complicada, pero eso va a ser así, ¿ya? Independiente de eso, que pueden haber otros ejercicios optativos que permitan subir los puntos, eso también. Mi idea de las tareas y de los quizzes es que a ustedes les sume, no que les pese, ¿ya? Así que cuenten con eso, que la próxima tarea no va a ser una carga, al menos no quiero que sea así. Eso, ¿alguna otra pregunta de la materia o del curso? Sí, Cristian, ¿alguna otra pregunta? Ok, si no hay más preguntas, terminamos acá por ahora. Ah, el envío de la escritura es aparte de todo lo otro. Sí, lo dije al principio, voy a aprovechar de repetirlo. Eh, yo no sé lo que hace la universidad con los test de inglés, ¿ya? Yo solo sé que este curso tiene que evaluar su capacidad de escribir en inglés. Y para eso se les pidió escribir un pequeño párrafo y eso yo lo remito a la universidad. Y ellos me tienen que avisar todavía cómo les fue, quién aprobó, quién necesita ayuda, quién necesita revisar. ¿Ya? Yo no tengo idea la universidad de qué otras formas evalúa el inglés. No sé si que tienen que entregar en este curso y en otros más. No lo sé. Sé que tienen que tomar 3 cursos, ¿cierto? En inglés. Me imagino que no son simultáneos, la verdad que no lo sé. Así que sí, en el fondo lo que pasa en este curso es independiente de otros cursos. Así que eh, mucha gente no envió esa tarea. Y yo no sé, lo dije al principio, no sé bien qué significa eso, no sé bien qué va a pasar. Y al preguntar a la universidad, oye, ¿qué hago con la gente que no envió? No sé si la gente que no envió votó el curso, ya no es parte del curso, o solamente se les pasó, no lo sé. Así que, por favor, estén atentos con las tareas, porque esto es un requisito más del curso. ¿Ya? Es una habilidad que hay que evaluar y yo no la puedo evaluar si ustedes no envían sus tareas. ¿Ya? Así que, sí, yo no he tenido feedback todavía de la universidad. La universidad me tiene que decir de estos que enviaste, todo esto, quizás ustedes saben esto mejor que yo, hay 3 categorías, hay como suficiente o deficiente o no sé qué. Y hay una categoría que dice, ok, esto está, no hay problema, y hay otras categorías que te van a pedir, no, esto hay que escribirlo nuevo, incluso te van a ayudar a decir, mira, fíjate en esto, y qué sé yo, ¿ya? Así, pero yo necesito ese feedback, esa evaluación no la hago yo, la hace gente en la universidad que es especialista en esto. Así que yo ahí estoy a la espera. Yo les voy a comunicar cualquier noticia que yo tenga y voy a tratar de apretar a la universidad para saber qué es lo que están haciendo, ¿ya? Cuando vamos a tener resultados. Así que eso por ese lado. ¿Alguna otra pregunta antes que terminemos? Muy bien. Muchas gracias. Gracias a todos. Nos vemos el próximo lunes. Ustedes tienen ayudantía este jueves. ¿Ok? Así que saludos a
Bueno,
todos.
profe,
Ah, dime. Ah, ya.
adiós, me estás despidiendo. Chao, profe.
Ok. Chau, chau.